The modern global energy economy is fundamentally underpinned by a profound and highly orchestrated mastery of molecular physics, thermodynamics, and extreme thermal engineering. At the very center of this complex global system lies natural gas, a fossil fuel composed almost entirely of methane. In recent decades, natural gas has ascended to become the vital, indispensable baseload power source for the ongoing transition away from heavier, more polluting hydrocarbons like coal and heavy fuel oil. However, in its natural, ambient, gaseous state, methane presents a formidable, almost insurmountable logistical challenge for intercontinental trade. It is highly diffuse, occupies enormous physical volumes, and has historically been tethered to the strict physical geography of rigid cross-continental pipeline networks. The ultimate solution to this geographic tyranny is the cryogenic miracle of liquefied natural gas, a highly energy-intensive industrial process that relies on extreme refrigeration to fundamentally alter the physical state of the molecule, thereby unlocking global maritime trade and reshaping the geopolitical map of energy distribution. Understanding the logistics of this multi-trillion-dollar industry requires a deep foundational appreciation for the thermodynamic realities and the sheer mechanical effort required to cool methane to its liquid state. Natural gas must be systematically brought down to an astonishing temperature of -162 degrees Celsius or -260 degrees Fahrenheit at standard atmospheric pressure to achieve liquefaction. This is not a simple single-step chilling process. Rather, it requires highly sophisticated, sprawling industrial infrastructure capable of extracting immense amounts of heat energy while managing highly volatile fluids. Before the temperature can even be incrementally reduced, the raw natural gas extracted from the earth must undergo rigorous and uncompromising pre-treatment. Natural impurities such as water vapor, carbon dioxide, hydrogen sulfide, and heavy hydrocarbons must be meticulously stripped away in dedicated processing trains. If these elements were allowed to remain in the gas stream, they would freeze solid long before the methane liquefied, catastrophically blocking the intricate network of cryogenic heat exchangers, valves, and piping. Furthermore, trace elements like mercury must be completely removed to prevent severe metallurgical degradation, specifically the catastrophic corrosion of the aluminum components that make up the core of the liquefaction plant. Once thoroughly purified and conditioned, the gas stream enters the main cryogenic heat exchanger, an immense piece of vertical industrial architecture where the actual phase change occurs. The technology dominating this space relies heavily on cascade cooling methodologies or mixed refrigerant cycles. In these highly calibrated systems, a specific proprietary cocktail of light hydrocarbons, typically including methane, ethane, propane, and nitrogen, is compressed, cooled, and expanded in a continuous, multi-stage closed loop. This ingeniously exploits the Joule-Thomson effect and the principles of adiabatic expansion, a thermodynamic phenomenon where an expanding gas doing work against an external pressure cools down significantly, provided the system is heavily insulated against any heat gain from the outside environment. The mixed refrigerant absorbs the sensible heat from the natural gas stream, lowering its temperature degree by painstaking degree until it reaches the critical cryogenic threshold where the phase change becomes inevitable. At this juncture, the system extracts the latent heat of vaporization, a process that coaxes the rapidly vibrating methane molecules to slow down, lose their kinetic energy, and condense into a clear, colorless, non-toxic, and highly dense liquid. The reason this specific phase change serves as the absolute secret weapon in modern energy density and transport efficiency is purely mathematical, yet staggering in its implications. The liquefaction process reduces the physical volume of natural gas by an astonishing factor of 600. To properly visualize this scale, a volume of natural gas that would entirely fill a massive commercial skyscraper in its gaseous state is condensed into a volume of liquid that could easily fit within a single standard shipping container. This volumetric collapse is the foundational economic engine of the entire global gas trade. It allows massive, unprecedented quantities of thermal energy to be concentrated in the insulated holds of specialized ships, entirely bypassing the need for fixed, multi-billion-dollar transnational pipelines that are often vulnerable to political disputes and sabotage. The resulting liquid can then be transported thousands of miles across open oceans to supply energy-hungry islands, remote coastal regions, or entire nations seeking to radically diversify their energy portfolios away from neighboring pipeline monopolies. However, the thermodynamic challenge does not safely conclude at the export terminal's liquefaction plant. It merely shifts from the shore to the high seas. Maintaining these ultra-low temperatures across thousands of miles of unpredictable open ocean presents a constant, grueling battle against the fundamental laws of thermodynamics. Heat from the ambient ocean water and the atmosphere relentlessly attempts to penetrate the heavy insulation of the cargo tanks. Because it is both economically and mechanically impractical to actively refrigerate the entire massive cargo space of a moving vessel down to -162 degrees Celsius using traditional mechanical chillers, the maritime industry relies on a brilliant physical phenomenon known as auto-refrigeration, which is managed by the continuous generation of boil-off gas.
As thermal energy inevitably leaks through the heavy insulation of the ship's containment tanks, it is absorbed by the liquefied natural gas sitting at the extreme boundaries of the containment system. This continuous heat ingress provides the exact amount of latent heat necessary for a small, predictable fraction of the liquid cargo to vaporize back into a gas. Because vaporization is an inherently endothermic process, meaning it absorbs surrounding heat to facilitate the phase change, the evaporation of this small amount of methane effectively cools the remaining bulk liquid in the tank, maintaining the vast majority of the cargo at its cryogenic boiling point. The engineering mathematics behind this are precise. For a standard 140,000 cubic meter tank, the heat leakage value is approximately 169,919 watts, equating to 169.919 kilojoules per second of energy entering the system. Fascinatingly, as the capacity of the tank increases to, for instance, 200,000 cubic meters, the heat leakage rate structurally decreases to around 163,253 watts due to the improved surface area to volume ratio, demonstrating the thermodynamic efficiency of building ever larger vessels. This newly formed vapor is known universally in the industry as boil-off gas, and managing it safely is one of the most critical, complex aspects of cryogenic marine engineering. If left unchecked and unmanaged, the continuous generation of boil-off gas would cause a rapid, highly dangerous pressure buildup within the sealed containment tanks, eventually compromising the structural integrity of the vessel and leading to catastrophic failure. The engineering solutions developed over the past 6 decades to manage this boil-off gas, meticulously balance the internal tank pressure, and utilize the vapor safely have driven the spectacular evolution of the specialized vessels that carry this concentrated energy across the globe. The vessels tasked with transporting liquefied natural gas are unquestionably among the most complex, highly engineered, and expensive commercial ships ever constructed by human hands. Since the inaugural, highly experimental voyage of the Methane Pioneer in 1959, which carried a mere 5,500 cubic meters of cryogenic cargo, the scale, sophistication, and capacity of the global fleet have expanded at an exponential, breathtaking rate. The subsequent launch of the Methane Princess in 1964, utilizing early conch cargo containment systems made of 5083 aluminum alloy and balsa wood insulation, proved the long-term viability of the trade. Today, these modern giants of the high seas serve as floating cryogenic vaults designed to endure the punishing physical forces of the ocean, including massive wave impacts and violent storms, while delicately coddling a highly volatile, ultra-cold cargo. At the absolute core of their design is the cargo containment system, a marvel of structural engineering that must accommodate extreme thermal contraction while preventing any possibility of a catastrophic hull failure. The modern global fleet is predominantly divided between two distinct, competing engineering philosophies: the independent spherical Moss tanks and the integrated membrane containment systems. The Moss tank design, instantly recognizable on the horizon by the massive hemispherical domes protruding above the ship's main deck, utilizes robust, self-supporting spherical tanks typically constructed from specialized ultra-thick aluminum alloys. The inherent geometry of the sphere is its greatest engineering strength. It allows naval architects to achieve highly accurate predictions of stress distribution and fatigue life across all parts of the structure. This means the tank itself is incredibly resilient to the violent sloshing forces of the liquid cargo during rough seas, a phenomenon that can exert massive kinetic energy against the tank walls. Because of this supreme structural integrity, Moss tanks do not require a full, continuous secondary barrier to protect the ship's outer steel hull in the highly unlikely event of a primary leak. Instead, a partial barrier located beneath the sphere is fitted with a highly sensitive gas sampling system to catch and monitor any potential leakage. These massive spheres are supported entirely by a unique structural transition joint at their equator, which acts as a crucial thermal break, preventing the intense freezing cold of the aluminum sphere from transferring to and dangerously embrittling the standard carbon steel of the ship's hull. In stark contrast, membrane containment systems such as the widely adopted GTT NO96 and Mark III designs originating from French engineering firms are optimized relentlessly for maximum volume efficiency. Rather than using heavy, self-supporting independent tanks that leave empty voids within the ship's hull, the membrane design relies entirely on the ship's inner hull structure to support the immense hydrostatic and hydrodynamic cargo loads. The containment system consists of incredibly thin, flexible primary and secondary membranes, often made of Invar, a highly specialized nickel-steel alloy known for having a near-zero coefficient of thermal expansion, or corrugated stainless steel that can flex with temperature changes. These thin metallic liners are separated by extensive, highly engineered layers of insulation, traditionally utilizing plywood boxes meticulously filled with perlite powder or reinforced polyurethane foam. Because the membrane directly conforms to the rectangular, prismatic shape of the ship's hull, it utilizes the available physical space much more efficiently than a sphere, allowing for significantly higher cargo capacities within the exact same physical footprint. However, this trade-off for maximum volume comes at the cost of inherent structural rigidity. Membrane tanks are much more susceptible to the impact loads of liquid sloshing, requiring careful operational management of fill levels, and they require a complete, continuous secondary barrier to ensure the absolute safety of the vessel's hull. The relentless, industry-wide pursuit of economies of scale has culminated in the newest 2026 fleet of ultra-large carriers, spearheaded by Qatar Energy's unprecedented and historic shipbuilding program. Aiming to expand its logistical dominance with a fleet totaling 128 new state-of-the-art vessels, Qatar Energy has recently commissioned the construction of 24 QC Max vessels from China's Hudong Zhonghua Shipyard, a subsidiary of the China State Shipbuilding Corporation. These QC Max ships are the absolute largest liquefied natural gas carriers ever conceived or built, each boasting a staggering, almost incomprehensible cargo capacity of 271,000 cubic meters. The strategic deployment of these megaships, which represent a total contract value of approximately $8 billion and scheduled for delivery between 2028 and 2031, will drastically reduce the per-unit transportation cost of energy. This massive investment is perfectly synchronized to solidify Qatar's dominance as it aggressively aims to double its domestic production capacity from 77 million tons per annum to 142 million tons per annum through its massive North Field expansion projects. Managing a cargo of this unprecedented magnitude requires revolutionary approaches to handling the inevitable boil-off gas. Historically, earlier generations of liquefied gas carriers were propelled by highly inefficient steam turbines, primarily because the steam boilers provided a convenient, safe, and easily controlled method to dispose of the vaporized cargo by simply burning it for propulsion. However, the soaring economic value of the cargo itself, combined with the stringent modern regulatory demands for fuel efficiency and drastic emissions reductions, have rendered steam propulsion entirely obsolete for the newest megaships. The QC-Max fleet and the preceding Q-Max and Q-Flex vessels utilize highly efficient dual-fuel slow-speed diesel engines or advanced diesel-electric propulsion systems.
To deal with the massive volumes of boil-off gas generated by 271,000 cubic meters of liquid cargo without wastefully burning it, these modern leviathans are equipped with highly sophisticated onboard reliquefaction plants, typically supplied by specialized cryogenic firms like Wärtsilä Gas Solutions, Hamworthy, or Cryostar. These miniature shipboard cryogenic facilities capture the boil-off gas directly from the top of the tanks, compress it, and process it through an intensive cooling cycle. The most advanced systems utilize a closed-loop nitrogen expansion cycle, often referred to thermodynamically as a reverse Brayton cycle. In this intricate system, a dedicated inventory of high-pressure nitrogen gas is run through an expander, drastically dropping its temperature to around -162.5 degrees Celsius. This super-chilled nitrogen is then passed through a highly efficient cryogenic heat exchanger, or cold box, alongside the captured boil-off gas. The nitrogen absorbs the heat, condensing the vaporized methane back into a liquid state, while non-condensable elements like trace nitrogen are separated out. The newly liquefied natural gas is then safely pumped back into the cargo tanks. This technology not only conserves the highly valuable cargo over long intercontinental voyages, but also allows the ship operators complete independent flexibility in managing tank pressures regardless of the vessel's speed, prevailing weather conditions, or the specific fuel demands of the main propulsion engines. Maneuvering these colossal vessels into highly congested, complex global ports requires absolute precision, flawless environmental awareness, and rigorous regulatory oversight. The Society of International Gas Tanker and Terminal Operators, or SIGTO, has established highly stringent, globally recognized guidelines to systematically mitigate navigational risks. Port entry is a highly orchestrated, almost military-style operation. When a carrier approaches a terminal, it enters a strictly enforced exclusion zone, a dynamic bubble of clearance designed to keep all other maritime traffic at a safe distance and prevent any possibility of collision. Because of the immense mass and staggering kinetic energy of a QC-Max vessel, stopping and turning cannot be left to the ship's propulsion alone. The vessel must be intercepted at the harbor entrance by a fleet of specialized escort tugs, each typically requiring a minimum propulsion capacity of 3,000 horsepower to exert the necessary physical control over the behemoth. These heavy tugs are carefully tethered to the extreme forward and aft centerlines of the carrier, physically guiding the ship through narrow approach channels. The final berthing process is a masterclass in slow-motion physics. The carrier must be brought parallel to the unloading terminal at a distance of about 50 meters and then delicately pushed laterally against the pier using breast and spring lines. To prevent any structural damage to the berth's sophisticated fendering system or the ship's vulnerable hull, the maximum permitted contact speed is meticulously controlled, often capped at a mere 10 centimeters per second. Only through this extreme marriage of heavy engineering and delicate seamanship can the global supply chain function safely on a daily basis.
Once the liquefied cargo has safely arrived at its destination port, the entire complex thermodynamic process that occurred thousands of miles away must be systematically reversed to integrate the massive payload of energy into the domestic, industrial, and residential grid. This pivotal process, known as regasification, is the mechanical and thermal act of warming the cryogenic liquid back into a high-pressure gas without losing energy efficiency or causing catastrophic mechanical failures due to thermal shock. Unlike the highly energy-intensive process of liquefaction, regasification primarily requires an abundant source of ambient heat and tremendous, highly engineered fluid pressure management. At a traditional, large-scale coastal import terminal, massive mechanical unloading arms connect directly to the ship's midship manifold, transferring the liquid via heavily insulated pipelines into double-walled, full containment storage tanks situated onshore. From these massive cryogenic reservoirs, the liquid is drawn into the primary processing system. Because the regasified natural gas must eventually be injected into the domestic pipeline network at extremely high pressures, often ranging between 80 to 120 bar, to ensure it reaches users hundreds of miles inland, it is a fundamental engineering reality that it is far more energy efficient to pressurize the fluid while it is still in its dense liquid state. High-pressure booster pumps take suction from the storage tanks and from a boil-off gas recondenser, utilizing the physical properties of the dense liquid to achieve immense pressures with a fraction of the mechanical energy that would otherwise be required to compress a vast volume of gas using standard compressors.
Once highly pressurized cryogenic liquid enters the vaporizers, the thermal heart of the plant. Coastal terminals frequently utilize highly efficient open-rack vaporizers or submerged combustion vaporizers. In an open-rack system, the high-pressure liquid methane flows upwards through a series of specialized finned aluminum tubes, while vast quantities of ambient seawater are pumped and sprayed continuously over the exterior of the panels. The immense temperature differential between the comparatively warm seawater and the extreme cryogenic liquid inside the tubes causes the seawater to rapidly surrender its heat. This thermal transfer flashes the liquid methane inside the tubes back into a gaseous state, warming it rapidly from negative 162 degrees Celsius to roughly positive 10 degrees Celsius. The newly reanimated gas is then precisely metered for commercial accounting, odorized if required by local regulations, and injected seamlessly into the invisible grid of subterranean pipelines. From there, it flows outward, powering heavy factories, generating electricity in combined cycle power plants, and heating homes across entire continents. While immense, concrete and steel onshore terminals have been the historical standard for importing nations, the strategic landscape of energy deployment has been radically and permanently transformed over the last decade by the rapid rise of floating storage and regasification units, or FSRUs. An FSRU is essentially a highly specialized vessel equipped with both massive cryogenic storage tanks and entirely self-contained onboard regasification modules. These floating terminals act in all functional aspects exactly like land-based infrastructure, but offer unprecedented, game-changing strategic flexibility. Constructing a massive onshore regasification terminal is a capital-intensive, high-risk endeavor, fraught with complex civil engineering challenges, stringent environmental permitting hurdles, and lengthy construction timelines that typically stretch from 4 to 6 years before a single drop of gas is delivered. In stark contrast, a bespoke FSRU or a swiftly converted conventional carrier can be deployed, moored, and fully connected to a high-pressure subsea pipeline or a simple dockside manifold in just 1 to 3 years. This rapid deployment capability has made FSRUs the ultimate tool for developing nations seeking swift, reliable access to cleaner energy, or for established economies requiring immediate supply security buffers against geopolitical shocks. By permanently mooring an FSRU at a protected harbor, a specialized cross-dock facility, or an offshore single-point mooring buoy system, a nation can instantly tap into the global liquefied natural gas spot market without waiting half a decade. The operational capabilities of these vessels are staggering. They are capable of continuous high-volume output, perfectly matched to national grids. For instance, specialized FSRUs can deliver regasified natural gas at exact pipeline pressures with continuous flow rates ranging from 690 million to well over 1,200 million standard cubic feet per day. The seamless integration of these floating assets with high-pressure pipeline networks ensures a reliable industrial power supply, providing the massive volumes of natural gas required to prevent power grid collapse during peak winter demand, or to fuel energy-hungry coastal industrial zones, thereby totally circumventing the delays and rigidities of historical terrestrial infrastructure.
The rapid proliferation of regasification technology, particularly the highly agile deployment of floating terminals, has fundamentally rewritten the geopolitical rulebook of global energy security. For decades, the uninterrupted flow of natural gas was dictated almost entirely by the physical geography of rigid cross-continental pipelines. This hard, immovable infrastructure created captive markets, functionally locking importing nations into inflexible 20 to 25-year take-or-pay contracts, often punitively pegged to completely unrelated oil-indexed pricing mechanisms. More critically, this pipeline-centric dependency left entire geographic regions highly vulnerable to sudden supply shocks, catastrophic technical disruptions, and the overt political weaponization of energy by monopolistic suppliers. The advent of a highly liquid, globally traded gas market transported by ships rather than steel tubes allows nations to sever these fixed dependencies, fundamentally decoupling their economic stability from the diplomatic whims of a single geographic neighbor. No single nation exemplifies this strategic paradigm shift more aggressively or successfully than Turkey. Historically, the Turkish national energy grid was acutely vulnerable, importing nearly 99% of its natural gas via long-distance pipelines from Russia, Iran, and Azerbaijan. This legacy architecture left the nation completely exposed to recurring technical failures, such as the severe pressure drops routinely experienced in the Iranian transmission system during peak winter demand periods, as well as the broader geopolitical leverage frequently wielded by Moscow. However, following the decisive adoption of its national energy and mining policy in 2017, Turkey executed a massive, highly calculated pivot toward liquefied natural gas infrastructure to achieve what it termed the doctrine of localization and diversification. By aggressively expanding its fleet of floating storage and regasification units, Turkey created a strategic redundancy that fundamentally altered its negotiating leverage on the world stage. State-owned operator Botaş commissioned the domestically flagged Ertuğrul Gazi FSRU, mooring it in the southern province of Hatay. The technical specifications of this vessel perfectly illustrate its strategic weight. Measuring 295 meters in length, the Ertuğrul Gazi boasts a massive storage capacity of 170,000 cubic meters and a staggering daily regasification capacity of 28 million cubic meters. This single vessel is capable of meeting over 8% of Turkey's entire daily national demand, heavily mitigating the severe risks associated with erratic pipeline flows from Iran, while supplying heavy industry in the Iskenderun Bay area. Concurrently, the deployment of the Vasant FSRU at the newly constructed Saros terminal in the northwest positioned a massive 5.6 million tons per annum influx of regasified fuel near the industrial heartland of Istanbul and the borders of the European Union. This massive infrastructure redundancy is not merely a defensive security buffer, it is proven to be a highly effective, aggressive commercial instrument. By 2025, Turkey had increased its daily regasification capacity approximately five-fold to an immense 150 million cubic meters, allowing it to cover roughly half of its peak winter demand using ships alone. This capacity became highly weaponized as a massive expiry wall of over 40 billion cubic meters of legacy 20-year pipeline contracts with Russia and Iran approaching expiration between 2021 and 2026. Because Turkey now possessed the physical capability to substitute rigid pipeline molecules with flexible spot market cargoes from the United States or Qatar, it was no longer a captive buyer. Botaş utilized this leverage to dismantle historical oil-indexed pricing, forcing pipeline suppliers to accept highly favorable hybrid, market-based formulas tied to the Dutch TTF or the US Henry Hub, and extending Russian contracts for only 1 year at a time to maintain total optionality. Furthermore, this physical diversification has allowed Turkey to physically integrate its national gas grid with Balkan markets, enabling lucrative physical exports to Bulgaria, Hungary, Romania, and Moldova, thus transforming the nation from a vulnerable transit corridor into a highly influential regional gas trading hub. The strategic importance of these maritime corridors and regasification nodes is further magnified by the intense, highly volatile regional instability characterizing the Eastern Mediterranean.
The discovery of massive deep-water gas fields, such as the 80 trillion cubic feet identified across fields like Leviathan off the coast of Israel and Aphrodite near Cyprus, initially sparked immense diplomatic hopes that shared energy wealth could catalyze regional peace and offer the European Union a permanent alternative to Russian supply. However, deeply entrenched geopolitical tensions, overlapping exclusive economic zone claims, and the stark reality of immense infrastructure deficits have severely complicated these lofty ambitions. The Eastern Mediterranean ecosystem suffers from a critical lack of export pipelines to move the gas to eager markets. High-profile plans for a 340-kilometer undersea pipeline connecting the Cypriot Aphrodite field to Egypt's established onshore liquefaction facilities in Idku have repeatedly stalled. The high capital costs, combined with the fact that Cypriot gas is dry and expensive to process for liquefied export, makes the economics highly challenging. Furthermore, the ongoing war between Israel and Lebanon, combined with the devastating conflict in Gaza, has injected severe risk premiums into the region, threatening existing energy agreements and stalling multinational corporate investments in future exploration. Consequently, the market is witnessing a distinct shift toward alternative, highly flexible export methodologies. Energy majors like Chevron are increasingly analyzing the viability of linking offshore fields directly to independent floating liquefied natural gas facilities, bypassing the severe geopolitical risks of piping gas through neighboring terrestrial territories entirely. While these floating plants have lower overall capacities, perhaps 9 billion cubic meters per year compared to 17 in Egypt's terrestrial facilities, they offer the ultimate geographic and political flexibility, allowing producers to load cargo directly onto outbound ships destined for hungry Asian or European markets without relying on unstable transit states. In this highly volatile landscape, the ability to liquefy, ship, and regasify energy without touching contested land borders remains the ultimate mechanism for ensuring immediate baseload power security. As the global community attempts to desperately balance the immediate, undeniable requirement for baseload industrial power with the long-term existential transition toward carbon-neutral fuels, the liquefied natural gas industry finds itself standing at a highly complex technological crossroads. While natural gas undoubtedly burns cleaner than coal or heavy marine fuel oil, producing zero sulfur oxides and significantly lower nitrogen oxides, the entire logistical chain, from wellhead extraction and intense liquefaction to intercontinental shipping and regasification, carries a substantial and heavily scrutinized carbon and methane footprint. To secure its ongoing role as the ultimate stabilizer for the global energy equilibrium in the coming decades, the industry is heavily investing in radical innovations designed to achieve zero-emission shipping and strictly carbon-neutral supply chains. The regulatory environment is tightening rapidly, forcing unprecedented innovation. The International Maritime Organization's strategic push towards absolute decarbonization includes the highly anticipated development of a net zero framework, heavily debated for adoption leading into 2026, which aims to enforce strict, progressively tightening greenhouse gas fuel intensity metrics across all global fleets. In response to this looming regulatory pressure, the maritime sector is aggressively pioneering the development of onboard carbon capture and storage technologies. OCCS represents a vital, immediate retrofit pathway for the existing fleet of carriers, ensuring that multi-million-dollar assets launched today remain commercially viable into the 2030s and 2040s without violating punitive international emissions penalties like the EU ETS or Fuel EU Maritime. The mechanical premise of integrating OCCS on a moving ship is highly complex. Post-combustion solvent-based systems are physically integrated into the ship's exhaust stacks to chemically scrub carbon dioxide directly from the engine emissions. However, capturing the gas is only the first major hurdle. The captured carbon must then be separated, heavily compressed, liquefied into a dense state, and stored in dedicated intermediate tanks on board the vessel until it can be safely offloaded to a certified permanent geological sink. This process introduces significant, often debilitating engineering compromises. The separation and liquefaction of carbon dioxide require an immense parasitic energy load from the ship's auxiliary generators, creating a highly counterproductive cycle where more fuel must be burned simply to power the capture equipment, severely impacting the vessel's overall efficiency. Furthermore, the bulky capture modules and heavily pressurized storage tanks consume highly valuable cargo space and weight allowances. Remarkably, the specific cryogenic physics of liquefied natural gas carriers provide a unique, highly synergistic solution to this severe energy penalty. The cryogenic liquid cargo inherently possesses a massive amount of cold exergy, typically between 800 and 900 kilojoules per kilogram, due to its extreme -162-degree temperature. Typically, this immense reserve of cold energy is entirely wasted, simply dissipated into the ocean or the air during the warming phase of the fuel delivery system to the ship's engines. However, highly innovative thermodynamic engineering now allows this cold exergy to be harvested and directly applied to the carbon capture cycle. By strategically routing the cold energy of the fuel to the refrigeration loops of the carbon capture system, the captured carbon dioxide can be liquefied with dramatically lower mechanical energy consumption.
Advanced thermodynamic simulations have proven that integrating the cold energy of the fuel can increase total exergy efficiency to over 45%, drastically reduce the specific power consumption of the liquefaction process, and achieve astounding carbon capture rates of 99.93%, dropping the efficiency penalty from an unacceptable 14.34% down to a mere 3.51%. This integration makes the economics viable, lowering the unit carbon capture cost to approximately $14.24 per ton. Despite these magnificent technical triumphs, the ultimate scalability of OCCS remains heavily dependent on downstream infrastructure. Captured carbon is only a true environmental asset if there is a robust, verifiable chain of custody for offloading the liquid into permanent geological sinks at major transshipment hubs like Rotterdam or Singapore. While maritime engineers focus obsessively on scrubbing emissions at sea, the onshore sector is attempting to address the carbon intensity directly at the source. Massive coastal liquefaction terminals in the United States and the Middle East are increasingly proposing the integration of carbon capture and sequestration technology directly into the export process, marketing the resulting product as green or carbon-neutral cargo. By capturing the heavy concentrations of carbon dioxide that must inherently be stripped from the raw wellhead gas during the pre-treatment dehydration and sweetening phase, operators can inject the greenhouse gas deep into subterranean saline aquifers near the export facility before the gas is even liquefied. While environmental critics correctly note that this captures only a fraction of the total life cycle emissions, ignoring the eventual combustion of the fuel by the end user, it nonetheless represents a highly vital, immediately actionable reduction in the overall emissions profile of the global gas trade. Simultaneously, the sheer physical footprint of the industry is rapidly shrinking, democratizing access to the fuel through the rise of small-scale, highly modular infrastructure. Historically, engaging in the liquefied gas trade required multi-billion-dollar investments in sprawling mega-terminals, effectively locking out smaller economies, remote industrial zones, or stranded gas fields that lacked the capital to participate. Today, advanced engineering has successfully condensed the entire complex liquefaction capability of a large-scale plant into highly compact, transportable, plug-and-play modules. Systems such as the patented CryoBox or advanced microscale plants utilizing revolutionary zero-refrigerant technology, which brilliantly use the high pressure of the raw natural gas feed itself as the primary cooling medium through a system of expanders, can be manufactured off-site, delivered by truck, and installed directly at the wellhead or attached to local pipeline spurs with minimal civil engineering. This high degree of modularity allows for fractional capital expenditure, significantly minimized risk, and drastically accelerated implementation timelines. If local energy demand increases over time, additional identical modules, such as the NMBL system, which can scale from 0.8 up to 2 million tons per annum, can simply be bolted onto the existing array to scale production efficiently without requiring entirely new facility designs. These compact systems enable a vibrant, highly dynamic virtual pipeline ecosystem, where small volumes of high-density liquid fuel are loaded directly onto specialized cryogenic tanker trucks or rail cars and driven to off-grid mining operations, remote island communities, or satellite regasification stations.
By cleverly leveraging the 80 to 90% energy efficiency gains of pumping the fuel in its dense liquid state rather than compressing gas into heavy steel cylinders, the virtual pipeline bypasses the grueling permitting processes, massive capital limitations, and tense geopolitical roadblocks of fixed terrestrial infrastructure entirely. In conclusion, the astounding technical ability to shrink a hydrocarbon molecule by a factor of 600 through extreme refrigeration has birthed a logistical network of unparalleled strategic value. As the global economy rigorously navigates the tumultuous transition towards renewable power generation, the inherently intermittent nature of solar and wind power absolutely necessitates a highly reliable, instantly dispatchable baseload fuel to prevent grid instability. The unmatched flexibility of the liquefied natural gas market, facilitated by massive cryogenic carriers, agile floating regasification units, and the rapid integration of advanced carbon mitigation and modular technologies, ensures that vital energy can continuously flow around geographic choke points and political blockades. By successfully divorcing the molecule from the steel pipeline, the liquefied economy remains the ultimate indispensable stabilizer for the global energy equilibrium in an increasingly fractured and complex world.